Welcome back, AP Chemistry students, to Unit 2, Chemical Bonding. Today we'll be talking about Unit 2.3, Valence Shell Electron Pair Repulsion Model, or VSEPR for short. The VSEPR model allows us to predict the molecule's shape, and from that we can get its polarity, which is a big part of our next unit, intermolecular forces. So this is critical for you to understand why water has a positive or negative end, or why oil is a liquid while other organic compounds are solids. So let's go over the valence shell electron pair repulsion model. Before we do, we have to get a couple vocabulary words out of the way. In a bond, a region of electron density is a location around the nucleus where an electron can be. Now, a region of electron density is any lone pairs or bonded pair around a central atom. So in ammonia, there are 4 regions of electron density. In something like, say, carbon dioxide, carbon's electrons can be either in this double bond or this double bond, so there are only 2 regions of electron density. Regions of electron density are places around the central atom where you find electrons. Doubles, triple bonds count as only 1. Now, when these atoms form this bond, the way that happens is that they push together their orbitals. They kind of mush them together to make room for all these shared electrons. The mushing together of these regions means that we have to hybridize their orbitals. And hybridization is a lot more complicated than that. For this class, for my content in AP Chemistry, you don't have to be able to explain hybridization beyond saying, if you have this many regions, you have this hybridization. The orbitals that hybridize are your valence shell, since valence shell electrons are what are used in bonding. So the shells we have to play with are our s and p orbitals. If we have lots of regions of electron density, we might start pulling in d orbitals, but that only happens with large elements, so things after magnesium on the periodic table. For each region of electron density around a central atom, you need to hybridize an orbital. So if we have 2 regions of electron density, that means we need to hybridize 2 orbitals, and they're hybridized in the order in which they fill. So an s orbital always fills first, then we'll hybridize and pull in a p. So anything with 2 regions of electron density, we would say is sp hybridized. If something has 4 regions of electron density, we'll have to pull in 4 orbitals to hybridize. So you would need an s and 3 of your p orbitals, or you would write this as sp3 hybridized. In a large molecule, something like xenon trifluoride. The xenon's electrons can be in any one of these single bonds or in the lone pairs. That would be 5 regions of electron density. So we are going to need to hybridize 5 orbitals. So we'll use sp and one of the d's, because xenon is able to pull in a d orbital. So 5 regions of electron density would be s, 3 p's, and a d, or sp3 dehybridized. You could write the d orbital at the end of a hybridization. It is just as correct to write it at the beginning. It's simply a matter of which your professor prefers or what they teach you. It's just a matter of what fills first. Long story short, put the d orbital either at the end or at the beginning of your hybridization. With that in mind, in class, I would have given you 20 balloons and you were to fill them up as close as possible, because electrons are negative, they take up space, they're going to repel one another. And in three-dimensional space, that repulsion is going to give them a particular geometry. Unfortunately, since you are watching this, you are most likely not in class, and so you didn't get to play with all 20 balloons and then run around the building with 20 balloons for the rest of the day. So towards that end, we're going to use the simulator we used in class, and we'll use the Lewis structures from page 11 in your packet. In order to complete this section of notes, you need to have valid Lewis structures for all the molecules on page 11. If you do not have valid Lewis structures yet in pencil, just in case you get any wrong, please pause the video and draw your Lewis structures. I will assume that you have valid Lewis structures in each of these boxes. Take up a sizable amount of the box, but leave some space because we have some notes we are going to take here as well. Carbon dioxide is an example of a molecule with two regions of electron density. Electrons can be either on the left or right hand side in each of those double bonds. Having two regions of electron density means that carbon dioxide is an example of something that is sp hybridized. Being sp hybridized, these bonded electrons are going to repel one another. And since they repel one another in three-dimensional space, they'll take up as much room as possible. So they will look something like this. This shows that they are 180 degrees from one another. And because they are in a straight line, this shape is called linear. The simulation we're using, by the way, is from fetcolorado.edu. Feel free to find this molecule shape simulator and tinker with it. Look at some of the molecules we've looked at. As you can see, I can move and manipulate them. This is an excellent simulator to practice these molecular geometries, which you need to have memorized. So carbon dioxide has a bond angle of 180 degrees. It is an example of something that is linear. So in your box, in your notes, pretty much on page 11, fill in both the bond angle and the hybridization while I talk a little bit. The hybridization, personally, I remember hybridization with the bond angle because it's easier to remember just 5 bond angles than it is to remember all 11 that are on this page. So for me, I remember anything that is sp hybridized has a bond angle of 180 degrees. We call it linear. And this goes for things that are binary as well. Hydrochloric acid, while having 4 regions of electron density, would still be a linear shape. The hybridization would be different, but this is an example of something that obviously is going to be 180 degrees. So anything binary or anything with 2 regions of electron density is a linear molecular geometry. We will eventually talk about how these geometries lead to a polarity, a dipole moment that can attract positive to negative ends. But that is the next unit where we will come back to this example. Anything with 3 regions of electron density means you would need to have 3 orbitals hybridized. So s and 2 p's or sp2 hybridized. Boron trifluoride, or boron with 3 of anything, is always going to have the same shape, since boron will always be satisfied with just 6 electrons around it. This creates a flat triangle. As an equilateral triangle, the bond angle for anything sp2 hybridized starts as 120 degrees. Being that it is a flat triangle, boron trifluoride, or anything with 3 regions of electron density and no lone pairs, is known as a trigonal planar shape. Now that's really the kicker here. 3 regions of electron density with no lone pairs is trigonal planar because it is sp2 hybridized. The bond angle is 120 degrees. However, the addition of a lone pair will change that bond angle and change that shape. So for sulfur dioxide, here is one valid Lewis structure for sulfur dioxide. If you took the time to look at formal charges, congratulations, you would have found the actual structure of sulfur dioxide, which would be double bonded to each oxygen. This lone pair that sulfur dioxide has, lone pairs are only attracted to a single nucleus and therefore have way more energy than bonded pairs, which are attracted to 2 nuclei. Those lone pairs with way more energy take up more space around the nucleus. They are going to repel the bonded pairs, and so the bond angle will always drop when you have a lone pair. Now, the exact amount it drops, you are not responsible for knowing. You just need to know that the bond angle of sulfur dioxide is less than 120. So something around the range of like 118, 119. Again, it's not a massive drop, and you are not responsible for knowing the exact amount that it drops, but you are responsible for knowing that lone pairs reduce the bonding. So here we see our example, sulfur dioxide, with the lone pair repelling the bonded pairs. Our bond angle drops to 119. It is no longer a flat triangle. It is now a bent triangle. So we simply call this bent. So anything sp2 hybridized has a bond angle of 120 degrees. It's a trigonal planar, but when you add a lone pair, it becomes a bent shape and the bond angle reduces slightly. 4 regions of electron density means we will have to hybridize 4 orbitals. So again, we will pull all 3 p's and an s. Anything with 4 regions of electron density is sp3 hybridized. Now, the reason I gave you balloons to practice this is because you would think, based on your 2-dimensional drawings of your Lewis structures, that these lay flat, that you have a flat square. However, in 3-dimensional space, that's not how it works. The greatest distance between 4 objects in 3-dimensional space is actually to set up a 4-sided dice. If any of you play Dungeons and Dragons, you're my people, man. A 4-sided dice is known as a tetrahedral. And the bond angle, the angles within a tetrahedral, are 109.5 degrees. So methane, 4 regions of electron density with no lone pairs, is a tetrahedral shape, and the bond angle is 109.5 degrees. So again, personally, I remember hybridization with the bond angle. Anything sp3 hybridized is going to initially start at 109.5 degrees. So the bond angle in methane, or carbon with 4 of anything, is always 109.5. And we call it a tetrahedral. Adding a lone pair is going to change the geometry and the bond angle. Lone pairs, remember, take up more space. They have more energy, so they're going to repel the bonded electrons. And again, you're not responsible for knowing the exact values, but you should know that it is slightly less than 109.5 when we get to ammonia. Ammonia's bond angle drops to 107.8. Again, you are not responsible for knowing the exact value, but you do need to know that this shape is different. We have a 3-sided pyramid, so we call this a trigonal pyramid. So anything with 4 regions of electron density and 1 lone pair takes on a trigonal pyramid shape. 2 lone pairs is going to drop that bond angle substantially. And substantially is still a relative term. It's not going to be very near 109.5. In fact, with water, it's 104.5 degrees. But again, you are not responsible for knowing that. You are only responsible for knowing that it is less than 109.5 degrees. In water, we get this Mickey Mouse looking shape. The lone pairs set up on the water and the bond angle drops. This is why water has a lot of the properties it has. This is a bent shape. And yes, that's the same as sulfur dioxide. The difference here is this is a bent shape with 4 regions of electron density. It's sp3 hybridized, whereas bent with 3 regions is sp2 hybridized. One quick note here, carbon is the basis of organic chemistry, and since it is so heavily studied in its own content, you may see methane and carbon-based compounds represented differently. This tetrahedral shape is so critical to organic chemistry that we represent it differently in some textbooks. When you see single lines, that means that the carbon and the next element are in the same plane as one another. However, if one of the bonds is coming towards you, we show it as a filled in triangle, right? Because when things come closer, they become more defined. If they're going away from you, they get blurrier, so things going away from you are shown as a dotted line. This is a way to represent two-dimensionally a three-dimensional concept. So if you ever see this, just if you're ever curious, that's what that represents. It's representing that tetrahedral shape in a three-dimensional way. We will talk more about organic compounds at the end of the year, but for right now, just so you know, just for your edification. In the interest of saving time and making your pictures less complicated than necessary, I'm not going to draw the complete Lewis structures for these because having all of those lone pairs on your terminal atoms is going to become messy very quickly. You should have them. Each one of these chlorines should have 8 electrons around it, including the one bonded pair, but again, for simplicity's sake. Phosphorus pentachloride has 5 regions of electron density. 5 regions of electron density means we need to start pulling into the D sublevel. So 5 regions would be sp3d hybridized. Again, the d orbital can be in front or behind of the hybridization. It is irrelevant. So d sp3 hybridized shapes will take that into account. And again, if you had balloons, you would see three-dimensionally and feel three-dimensionally how they would spread out. In the simulator, we can show this. This sets up actually kind of 2 shapes. You have a triangle on the top, a 3-sided pyramid on the top, and a 3-sided pyramid on the bottom. So this is known as a trigonal bipyramid shape. Being that it is a bipyramid, there are actually 2 bond angles for anything with 5 regions of electron density. Anything that is dsp3 hybridized technically has 2 bond angles. From the top of a pyramid to the bottom, that's 90 degrees. However, along the middle, where you have a triangle, that triangle lies flat, so it is 120 degrees along the middle. Anything that's dsp3 hybridized has 2 bond angles, 90 degrees and 120 degrees. Now those will change based on the lone pairs. Adding a lone pair is going to change the bond angles slightly. However, it's going to have drastic implications for the shape. Adding a lone pair, like we do in sulfur tetrafluoride, we still have those two shapes, right? This still looks like a three-sided pyramid. The lone pair occupies one of the sides of our pyramid, and we end up with this shape called a seesaw. The seesaw shape, the bond angle between top and bottom is still 90, but now the lone pair pushes that 120 to be slightly less than 120. Having two lone pairs actually makes your three-dimensional shape and your two-dimensional shape very similar. Chlorine trifluoride. Chlorine trifluoride has 5 regions of electron density, but with two lone pairs, the lone pairs occupy two sides of your triangle, and the only thing you're left with is a flat shape that resembles a T. So 5 regions of electron density with two lone pairs is called T-shaped. And we drop that other bond angle. The bond angle now is just the 90 degrees from one side of the T to the other. 3 lone pairs returns us to a golden oldie. The lone pairs will set up along this triangle part of our trigonal bipyramid, removing the pyramid and returning us to a straight line. So anything with 5 regions of electron density and 3 lone pairs, like xenon difluoride, returns us to a linear shape, where the bond angle is 180 degrees. And this is the only time that pairing a bond angle with a hybridization that won't serve you so well. 6 regions of electron density is as far as we will go in this class. 6 regions of electron density means we will have to pull in 6 orbitals, so we end up with sp3d2 hybridization. These large molecules with 6 regions of electron density have some of the least changes in their bond angles because of lone pairs. But let's get the first shape out of the way. Unfortunately, if you were in class and you had balloons, most likely you were unable to hold 6 balloons at the same time in one hand. So this shape kind of you just had to see in the simulator. With 6 regions of electron density, you end up with, so this looks like an 8-sided dice. 8-sided dice are known as octahedrals. An octahedral is an 8-sided dice. So the bond angle for this starts at 90 degrees from top to middle, and along the middle they're all going to be 90 degrees from one another. So anything that's sp3d2 hybridized starts with a bond angle of 90 degrees. Adding lone pairs is actually not going to substantially change that bond angle. In bromine pentafluoride, we end up with a square that forms a pyramid. The lone pair still repels the bonded pair, so the bond angle does drop, but this is known as a square pyramid with a bond angle that's a little less than 90 degrees. 2 lone pairs are going to set up opposite one another. Since they set up opposite one another, we end up with a flat square known as square planar, and they'll equally repel the bonded pairs, and so the bond angle actually doesn't drop with this molecular geometry. So we call this square planar because it's a square that lays flat in the plane of the nucleus. And with that, those are all the molecular geometries, hybridization, and bond angles that you are responsible for knowing. On the website for the class, you will find flashcards because you have to have these memorized. You have to be able to draw a Lewis structure. From that Lewis structure, determine the hybridization, and with the hybridization, come up with a molecular geometry. If you're ever asked to explain why bromine pentafluoride and phosphorus pentafluoride have different bond angles, You could say they're different shapes because they have different hybridizations. Hybridizations are a valid explanation for a shape and changing bond angles. If you're asked to explain why the bond angles of methane and ammonia are different, talking about the lone pairs is a valid explanation. You can relate that back to the hybridization, but you should talk about how lone pairs, since they are only orbiting a single nuclei, have greater energy and therefore repel bonded pairs. That is a valid explanation. This will be the end of Unit 2. I will most likely have a free response that you either did in class or you might have to do on AP Classroom. You also will have your personal progress check in AP Classroom to complete. Please complete your personal progress check and be ready for your Unit 2 test next class. I will see you in Unit 3.